Jump right in and tell everyone this is another ABG talk. And I kind of gave it that title because I know all of you at this point have had 1,000 ABG talks as my guess, and this is another one. And my hope is that this is the one that kind of drives it all home and you kind of get it and don't have to do it anytime after this. The other thing I want to mention is you're not going to see any charts on this. You're not going to see me making any like memorized charts up, down. I really don't like those because it doesn't get you to understand what's happening. It just promotes memorizing something, which I don't think is good, especially because when you're drawing ABGs, you're usually doing it in the ICU and patients are critically ill and you really need to have an idea of what's going on. So without further ado, let's get started with our another ABG talk. And the first thing that I want to mention before anything is defining terms. And defining our terms is not always the most fun thing. This whole talk in general is not the most fun thing, but important. An osis and an emia. Now, you hear this come up a lot. You hear people say, oh, they have a metabolic acidosis. They have a respiratory alkalosis. Osis and emia are different, and the verbiage matters. So an osis is a process. And emia, on the other hand, is the state of blood. And what we mean by that is you can have multiple processes happening at the same time. You can have a metabolic acidosis and a compensatory respiratory alkalosis. That's a very normal happening. So understanding that when we talk about this, the emia refers to specifically the pH of the person, where the pH falls after all of the osises are happening. And the osises are the processes that can happen at the same time. Okay? So emia, acidemia, or alkalinia refers to the patient's blood at the very end. The osis, as I said, metabolic, respiratory, acidosis, alkalosis, etc. So the other thing we need to establish is this equation, which is our bicarbonate buffer system equation. Carbon dioxide plus water yields H2CO3, which yields bicarb and hydrogen ions. And in this, we need to define two more things. And this is our acid, or our Lewis acid, which is a molecule capable of taking on an electron, in this case protons, which take on an electron to neutralize it. And our Lewis base, which is our bicarbonate here, okay? So the idea is pretty simple in that this equation is in an equilibrium. Now, that doesn't mean that you have equal amounts on each side. What it means is it is at a set point where the same amount is always going from this side to this side, and the same amount is always going from this side to this side. And when we throw that out of equilibrium is kind of when we change things around. I apologize. I'm going to get to all the questions at the end only because I want to kind of keep this flowing. So stick around and I'll answer it. We have our Lewis acid and our Lewis base. And so what happens is either our CO2 changes or our bicarb changes. Those are really the kind of two big things we're going to look at here. Okay? So any process, okay, an osis that involves, I know I got some pretty exciting colors going on here. An osis that is metabolic in nature is going to involve bicarb, and one that involves the carbon dioxide is going to be respiratory. I know I wrote that backwards. I apologize. I'm sorry for the dinging. We turn the sound off. So, if it involves a change in our bicarb from our normal, and remember, our normal bicarb is somewhere around 22 to 29, and our normal CO2 is about 38 to 42. So when we start to move outside of these normal values, that's when we call it an osis or an osis of either metabolic or respiratory nature. Okay? So that's the kind of first part. We've defined our terms. We know kind of what these things are, and we need to establish what's going to cause what. So anything that involves respiratory, like I said, is going to be CO2. So A respiratory acidosis is going to be one, and again, process, not endpoint, in which our CO2 rises. And the reason is, as you perturb one side, if your CO2 goes up here, the equation pushes to move the equilibrium back to the other side, and that's going to result in an increase in your hydrogen ions, which is going to increase the total acid in the blood. I'm sorry, someone's saying that the pink is hard to see. I won't write in the pink anymore. Metabolic HCO3, respiratory CO2. But like I said, as you increase your CO2, you're going to push the equation to the other side such that you liberate more hydrogen ions and have more acid in the blood. So a respiratory acidosis means you're increasing CO2. And a good example of this chronically would be something like COPD patients who hold on to that CO2, and you look at them and they have a normal bicarb or a normal CO2 that's baseline elevated maybe to the 60s. Another good example in the more acute might be narcotic overdose, where patients stop breathing, their CO2 acutely goes up, and all of a sudden they become supremely acidotic and then possibly acidemic if the buffer system can't handle it. Conversely, a respiratory alkalosis is going to be a decrease in our CO2, and this happens with hyperventilation, right? Patients who are breathing fast, you're having a panic attack, you put them on the vent and you're intentionally breathing them a little bit faster, that's going to cause a drop in our CO2. Now, the other side is our metabolic. Hey, brown isn't working so well, I apologize. Let's try metabolic and acidosis. And this is one of the most common things we're going to see, especially in the ICU. And this is going to be a drop in our HCO3 minus. So when do we see this most commonly? This is going to be with like elevated lactate in our infections or in bleeding or DKA. Things where you produce acid that's not part of this equation here, that's not part of normal CO2 moving to H+. So you produce lactate, you produce these kinds of things, and it binds your HCO3 minus, your bicarbonate, and it drops the level because now it's being bound. The next is obviously our metabolic alkalosis, and this happens when we have an increase in our HCO3 minus. And this happens usually chronically over time, say things to compensate for like a COPD or something like that, but may also happen with the exogenous administration of bicarbonate. Now, again, remember, all of these things, and I'm going to draw it in yellow because I want you to, or green, because I want you to remember, these are processes. And really what we're looking at when we call something an acidemia or an alkalinia is, if this is our little scale, do we have something that is more respiratory, acid, or do we have something that is more base? And whatever we land on, if our pH ends up being normal, 7.35 to 7.45, then we're normal. But if our pH is less than 7.35, we call this an acidemia, and if it's greater than 7.45, we call this an alkalinia. Again, because that's the end state of the processes that are happening. Like I said, you're oftentimes going to have patients who are in metabolic acidosis, who have an infection, they're producing lactate, etc., and then they start hyperventilating, so they produce a respiratory alkalosis to drop their CO2 to decrease their total acid burden, and wherever you land is where you are. Now, remember, the primary problem, you can never overcorrect, meaning if you have a primary metabolic acidosis, you cannot hyperventilate yourself to overcompensating back to going alkalemic. You will always either correct yourself to normal, like we see in COPD patients who have like a chronic CO2 of like 60 and a normal bicarb of like 50, a normal bicarb of like, 35, 40, and their pH is 7.38 and it's fine. But you don't overcorrect. You don't correct yourself back the other way. So now that we have these things, we got to kind of talk about, before we move into reading the ABG, the AGMA and NAGMA. okay? And I've written questions about this before, and you're going to see them again. And I know I'm running out of board space. I apologize. I will kind of move around some things. But an AGMA is an anion gap metabolic acidosis. Now, anion gap is very interesting because everyone knows that an anion gap, a normal one, is usually about 12. But where does that come from, right? And that's a big question that people tend not to talk about. Normal anion gap is 12, and that's because albumin in the blood carries a charge of about minus 2.5 to minus 3 plus other molecules. And so a normal albumin, as everyone knows or should know, albumin normal is about 4. So 4 times a charge of 3 gets you to a normal anion gap of 12, and that's where that difference comes up because we're not calculating that in. And so if a patient, let's say, has an albumin in the ICU of 2 and their gap is 12, people say, oh, no, he doesn't have an anion gap. Well, he does. His anion gap is actually 6 there because we've dropped his albumin by 2, and now his normal gap is not 12. So what are our causes of anion gap? Well, the easiest way to cause an anion gap is to throw more ions in that would increase the total amount of acid. So the usual thing that we use to talk about this is mud piles. I won't kind of write them all out, but methanol, toxicity, uremia or uric acid, so our BUN. D is for DKA or diabetic ketoacidosis when you produce ketones, polyethylene glycol, isoniazid, L is lactate, E is ethanol toxicity, and S is salicylates. And so any one of these can cause your anion gap metabolic acidosis. NAGMA, on the other hand, is when rather than increasing the amount of exogenous acid, instead what ends up happening is you replace bicarb with other negatively charged ions. A lot of times, chloride or something. I apologize, just write this HCO3 minus with things like chloride. So where does this happen? Well, we see this a lot when patients are vomiting a lot. So they're getting rid of all of their bicarb that's in their stomach, and it ends up causing a I apologize. You end up getting NAGMAs, for example, with fluid administration. So when you give high volumes of normal saline, right, you give this person all this chloride ions and your body sees negative charges and it gets rid of your bicarb because it says, well, we have this to be able to buffer. But remember that the chloride doesn't work the same way. The charge is seen the same, but the buffering action doesn't work in the same mechanism. So great. Now that we have that, we can talk about the delta-delta, which is the difference in our anion gap. So a normal anion gap, like I said, is 12. Wow, I really kind of ate through board space. I apologize. So let me get rid of this here and say our delta-delta, or our delta gap, is equal to our anion gap, which is whatever we have, minus 12, or our normal anion gap. And this is important because what the delta-delta says is, and we're going to run through a practice problem at the end to kind of illustrate all this, is that say you have an anion gap of 22, okay? That would make your delta-delta, we'll say 22, makes your delta-delta 10. Well, if your delta-delta is 10, that means that you have 10 extra acidic molecules in your blood, and as a result, your bicarb should drop by the same amount. And so if your normal bicarb is 22 and you have a delta-delta of 10, then your bicarb should now be 12. And if it's anything higher than 12, well, if it's 12, it means that you have strictly the anion gap acidosis. If it's higher than 12, it means that you have some type of metabolic alkalinia going on that's raising that bicarb artificially. And so I hope that kind of makes sense as a concept. So we check that. And then the last thing that we need to check before we go into a practice problem is our, God, am I running out of room to write things? I'm so sorry. Is our Winter's formula. Okay, so our Winter's formula reads as PCO2. So this is our expected PCO2 is equal to our bicarb, times 1.5 plus 8, plus/minus 2, okay? So when we plug in our bicarb, so patient has a metabolic acidosis, they're producing lactate, it's binding up all of our bicarb and it's dropping our bicarb. We expect our patient to hyperventilate in order to breathe off that excess hydrogen ions and to breathe off some of that acid. So we can predict in a sole metabolic acidosis with nothing else going on what our respiratory compensatory alkalosis will be in order to compensate. And so this is, we plug our bicarb in, we do our calculation, and it'll be somewhere in a range. So these are all kind of the things we look at, or that I look at, and many others when we're doing, evaluating an ABG. So I'm going to do some erasing real quick. This is so much easier on a computer. We're going to run through a practice problem because I know that's what you're all here for. That's kind of the fun stuff, is always participating in problems or answering questions. And I'll run through this real quick because I don't want to eat up too much of your time. I know you all have stuff to do. But we have a patient, and we'll say his sodium is 146. We'll say that his potassium is 3.2. We will say that his chloride is 100. And we will say his bicarb, and I'll write out his pH, and the way we write this is pH, CO2, O2, or PaO2 rather, and our bicarb. And so we're going to write this person as having the following numbers: 7.20. Our CO2 in this case is going to be 22. Our PaO2 is 90, and our HCO3 minus in this case is going to be 10. This is the problem we're working with, and we want to kind of take a step-by-step evaluation of how to kind of, work through this problem, okay? So the first thing that I do when I look at these problems is I say, okay, one, what's our pH? Oh my God, this is terrible colors. It's not showing up, we'll use red. One, I look at what is our pH? And in this case, our pH is 7.2. So this patient has an acidemia, right? Because it's below 7.35. Wonderful. You start off, patient has an acidemia. The next step that I look at is my CO2. Because if I have an acidemia and my CO2 is high, meaning they're going in opposite directions, if CO2 goes up and pH goes down, that means we have a primary respiratory acidosis. CO2 up, again, because CO2 going up is going to force the equation to the other side. So if my CO2 goes up and my pH drops, that means I have a primary respiratory acidosis. In this case, we look and we see that our CO2 is down. So I know that this person has, at the very least, a respiratory acidosis of some sort going on. Okay? Of some sort. Next, I look at my HCO3 and I do the same thing. What is our CO2 doing? Well, our CO2 is going up or down, and our bicarb in this case has also gone down. So I know that my patient also, in some way, has some type of, in this case, metabolic acidemia, or acidosis rather, because our HCO3 minus has gone down. Wonderful. So those are kind of like setting the stage. I know that the thing that's winning of all of the processes that are going on is an acidosis of some sort. I know that I have at least a primary, respiratory alkalosis. Oh my God, I misspoke. I'm so sorry. If I could fix this in editing post, I would. We have a respiratory alkalosis because our pH and our CO2 went in the same direction. Our CO2 went down. Apologies to everybody listening. COVID brain. So we have a respiratory alkalosis going on. We have a metabolic acidosis going on. And so what ends up happening is our emia, the state of the blood, is an acidemia, and that the metabolic acidosis is the thing that's winning. I know, I'm very sorry for everybody. I'm telling you, I've been a little fuzzy after getting COVID way back when, and I'm rallying back. But But what I'm saying is correct, kind of. So the next thing I'm going to go ahead and look at is my anion gap. Okay, so we've looked here, we have 146, 3.2, and 100. And so our anion gap in this case is going to be, we'll call it, I don't want to do decimals, so we'll just call this 4 for the sake of making things easier. And we will say that this patient's anion gap is 102, oh my God, is 104. Did I write this wrong? I might have wrote this wrong. Sorry. So our sodium is 146, our chloride is 100, and our bicarb is 10. So we have a gap of 36. Okay? I had the K there because when I did this in a previous problem, I was doing DKA, but we have our gap of 36. So our anion gap is 36, which is our difference between our positively charged ions and our negatively charged ions, predominantly chloride and bicarb. And then after that, we go on and we say, okay, 36. So we know that this patient has some large gap because they're producing lots of acid. And the next thing we want to see is the delta-delta. So do we have an appropriate drop in our bicarb for the acid that we've produced? Well, we have an anion gap of 36 and a normal gap is 12. So that means that our delta-delta is 36 minus 12 is 24. So that winds us up in a place where we have an inappropriate delta-delta compared to our bicarb here because we've only dropped 10. All right. And so the last thing we need to look at is our Winter's formula. And we want to see whether or not there's an appropriate change in our CO2 to deal with this acid. So we have our Winter's formula, like I said, up here. And we would plug in this case, I don't have a calculator on me, and unfortunately I'm not that good at mental math and I don't want to write it all out, but our PCO2 is 22, we said. I'm sorry, our bicarb is 10, times 1.5 is 15, plus 8, 23, and then plus minus 2 brings us about 21 to 25. That's our range. And so we know that, in theory, in this theoretical problem, that our PCO2 is appropriately compensated for this metabolic acidosis. And so when we look at our ABG, this is how I'm going to approach it. These are the steps I'm going to take. I'm going to look at my pH, my CO2. Oxygen is not so much important for your acid-base status unless you're thinking that the patient is hypoxic and therefore, that's why they're producing a lactate. And we look at our bicarb. And we treat it accordingly based off of, what is going on. If they have a metabolic acidosis, treat the reason for it. Treat the infection, give them blood if they're bleeding, whatever it is. And this way, now we have an establishment of when we can look at this ABG, because what we're going to go to next in our next series of talks is at some point talk about how to adjust our vent settings in order to accommodate this. So our patients who are on the vent, patients who we have come to the ICU who are hyperventilating and breathing 30, 40 times a minute with infections, we intubate them. What do? Sometimes we start them on a ventilator setting where their rate is like 12 because we think it's appropriate because that's normal breathing rate, but they're breathing fast for a reason. They're breathing because they're trying to get that acid off. So we want to start them at a higher respiratory rate. So this was another ABG talk.